Hello, everyone. This is your instructor, George Kutrakan, calling in or talking today again about the next chapter. Today, we're going to talk about Newton's second law of motion. And for those of you that are not familiar with this, Newton's second law contains much of the, or is probably the meatiest or the most significant of the three laws of motion. First of all, simply stated, it says that force on an object is equal to its mass times its acceleration. So we abbreviate that by saying F equals ma, and we'll talk about that throughout this chapter. So, in addition to the second law of motion, which I alluded to in the first slide, we are going to talk about how that force causes acceleration, how much acceleration it causes. We're going to talk about how objects accelerate under the force of gravity in free fall, when you drop a stone, for example. And then we will discuss what happens if we add another force to that object, such as friction. In the case of a free falling object like a stone, there'll be some wind resistance, and that wind resistance will contribute to its slowing down. And generally, friction operates in the opposite direction of the motion of the object. So we'll talk about friction as well. The distinction between mass and weight is uh, rather tricky. It takes some thought, and in 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 truth, we could say that Newton's second law is really required to understand that distinction between mass and weight. So we'll talk about that in the next few slides. Um, in this slide, we want you to observe that one of the first observations by Isaac Newton was that the acceleration of an object is directly proportional to the net force acting on it. So, if we think of a single force as probably the simplest case, we push an object with a certain force, then in the absence um, of any friction or other forces, we will observe that it will cause an acceleration. And furthermore, that if we double the force on the object, then its acceleration will also double. We characterize this or phrase this by saying that acceleration is directly proportional to the force. And notice that both of them are vector quantities as well. Force is a direction and magnitude. Acceleration has direction and magnitude. And we'll talk more about the direction of acceleration a little bit later. But generally, these are both true statements. And furthermore, to increase the acceleration of an object, um, we have to increase the net force acting on it. So this is the first observation of part of leading up to Newton's second law. In this slide, we're going to talk or begin to talk about the difference between the weight of an object and the mass of an object. The weight is a little bit easier to describe because we are all much more familiar with that in terms of understanding what that means in terms of using a scale that measures the mass of the weight of our luggage, that is to say how heavy it is, the weight of our bodies, the weight of our vegetables, and these are generally measured in units of pounds when we go to the grocery store or to the supermarket. So this force is a force that is due to the attraction of that object towards the center of the Earth, which is, in our experience, straight downward towards the direction underneath us, underneath the Earth. Mass is a little more complicated, but we will start by taking that same object that we may visualize. For example, it might be a steel ball that weighs 1 pound. If I want to know what the mass of that object is, then I need a way to do that. And as you can see in this slide, it says it's a measure of the inertia or sluggishness that an object exhibits in response to the response to the force that is applied to it. And so the way we quantify this, and we actually use Newton's second law, is to say if I apply a force of 1 pound on this steel ball and it begins to roll on a straight level surface, as long as I continue applying that 1 pound of pressure, it will accelerate, and I can measure the acceleration of the object. If the acceleration is very slow, then I know that the mass of the object is very large. And if the acceleration is very rapid, then I can know that the mass is very small. So what I'm going to do then to quantify the mass is to say if I take the force that I apply to this rolling steel ball, for example, and divide it by its acceleration, that will give me the mass. Now, while we are on Earth, weight and mass are proportional. In fact, we have conversion scales for them. You can weigh an object at, for example, 2.2 pounds, or you can put it on a scale that gives you the value in kilograms. And that works perfectly fine as long as we are making the measurement on Earth, because that particular scale is only calibrated for measuring the weight of the object while it is on Earth. So if I take this same lump of matter to the moon, we can say that it's got the same number of atoms and molecules in it, and therefore it has the same mass. But because the Earth, the moon, is so much lighter or less massive or smaller than the Earth, the weight of the object is much less on the moon. So, in that sense, if we went to the moon, the conversion from weight to mass would not be the same as it is on Earth. So, we can, of course, do this on Earth because we know that 2.2 pounds of weight, or an object that weighs 2.2 pounds, has a mass of 1 kilogram. And we can use that conversion and while we are doing the experiment here on Earth. But mass is intrinsically a different quantity. And it's easier to think of it as applying Newton's second law by saying, let's measure the mass by applying a force, measuring its response in acceleration, take the ratio, and that's what I'm going to call my mass. So we'll talk more about that in the next couple slides. Now, on this slide, we'll start as we did before by describing weight and its units. So usually the force on the object due to gravity is what we refer to as its weight, and the units that we are familiar with are the pound, which is the English unit. There is also what we call the metric unit or scientific unit, which is the Newton. So we can, by measuring the on a spring scale, attaching our weight or object to that, we can measure what the force of gravity is because we are opposing it with the spring on our weighing scale, and that spring will be distended as a result of the force of gravity. And when the spring has been extended to so that the force exactly balances the weight of the object, we can read the weight on the scale. So that's the idea of weight as a unit as a force and having the units we discussed. Mass, on the other hand, is a measure what we call the inertia or the resistance to change in motion. And the only way to really define it is to use Newton's second law. That is to say, as I said on the earlier slide, that if I push an object with a force of 1 pound and continually pushing on it, it will continue to accelerate. By measuring the acceleration and then taking that 1 pound divided by the acceleration, then I will get the mass of the object. And therefore, we can quantify it as or understand it as how rapidly does it change its velocity under the influence of a given force. And if it increases its velocity very, very quickly, then for 1 pound of force, then it will have a relatively small mass. On the other hand, if that 1 pound of force barely starts the motion at all, or makes the motion extremely slow or the acceleration slow, then I know I have a much massive object. So we can quantify that and say that the acceleration is inversely proportional to to the mass for a given force applied to it. Now, this slide just reinforces what I said in the previous slide, which is if I take a fixed quantity of force, like in my example, 1 pound, uh, then if I get a certain acceleration by applying that to for example, a steel ball rolling on the surface, um, if I apply that same force a to a steel ball that has twice the size, or we might say twice the mass, then the acceleration will be reduced because I have a much larger mass of object and it's much more sluggish or slow in its response to that force, and that is seen as reducing the acceleration. So as I double or triple the mass, then the acceleration will either half or go down by 1/3 of its original value. We characterize this by saying that acceleration is inversely proportional to the mass. That is to say that for a fixed amount of force, the higher mass has lower acceleration, and the lower mass has higher acceleration. Now, in this slide, we're going to talk about another property of moving objects, which is called acceleration. This was first formulated by Galileo by studying the speed of balls rolling down an inclined plane. And he was able to do measurements to determine how rapidly the speed changed as it went down the slope. And in particular, he could measure what was the change in velocity or speed of the particle after 1 second, after 2 seconds, after 3 seconds. And what he found was that the acceleration was the same regardless of what period of time that we looked at the ball, either in the first second of its motion, the second, or the third. So we come up with this concrete definition of acceleration as a change in velocity divided by the time over between which that final and initial velocity occurred. And so the units of that are going to be in units of meters per second, because if the change in velocity is in meters per second and we divide that by the time, then we get meters per second. We abbreviate that by calling that meter squared. So on this slide, you will see the equation at the bottom of the slide, the last line. It says that the force on an object that has a certain mass, where the mass is measured in kilograms, which, as you know by now, is, I'm sure, understand that kilo means 1,000 and kilogram is 1,000 grams. Um, that the that if I apply a force on a mass of a given number of kilograms, and I apply that force in newtons, that will result in a certain acceleration. So the units have to be taken care of to be very consistent. And in our work, we will work pretty much exclusively with the metric units, metric system, where the distance is measured in meters, the mass is measured in kilogram, and time is measured in seconds. Now, that equation then on the bottom says that the force in newtons is equal to the mass in kilograms times the acceleration in meters per second per second. The another statement, if we put that into English, we would say in the statement above it, the acceleration produced by a net force on an object is directly proportional to the net force, is in the same direction as the net force, and inversely proportional to the mass of the object that is being accelerated. So when we see F equals ma, we think I have a mass, someone is applying a force, it's resulting in an acceleration. And if we think in those terms, then it'll be much more easy to apply them to a problem that we want to work. A side note of this, by the way, is that the first law of motion from Newton is really embedded in the second law itself. Because if we look at the first law from chapter 2, objects in motion remain in motion unless a net force, unless a non-zero force is acting on it. And every object continues in a state of uniform motion or remains at rest unless acted on by a net force. So looking at this now, one can see that if you had known Newton's second law, that force equals mass times acceleration, then you would have been able to see that that when there is no net force acting on it, there is no net acceleration, and therefore the objects traveling at 5 meters per second will continue to move at 5 meters per second as long as no other force is acting on it. So that's just a little additional information that you might find helpful. This slide gives a concrete example of a calculation of acceleration. It states an example that we suppose that at one moment in time, the car's speed is 40 kilometers per hour, and at 5 seconds later, the car's speed is 45 kilometers per hour. So based on our definition, we can calculate the car's acceleration. The change in speed is 5 kilometers per hour, which occurs over 5 seconds of time. Therefore, the acceleration is 5 kilometers per hour per second. Now, this slide looks at the effect of taking an object and measuring its weight on Earth and applying that same object and measuring its weight on the moon. And since we should all agree that the mass of the object doesn't depend on where it's located, then we find that if, for example, we have an object that has a mass of 3 kilograms, it will weigh approximately 30 newtons on the Earth's surface. On the moon, however, that same 3 kilogram mass will weigh only 5 newtons, or about 1/6 of the of the of its weight on Earth. And the reason for that is that the mass of the moon is much smaller than the mass of the Earth. So if you go back to the previous slide, you can see that the acceleration of gravity on Earth is defined by the mass of the Earth. So if in that last equation I replace the mass of the Earth with the mass of the moon, I would get an acceleration that is about 1/6 as big as it is on Earth. Or to say it differently, it would be about um, approximately 2 meters per second, or 10/6, 10 divided by 6 meters per second. So the acceleration will be a lot less, and that's because it exists on the moon, and its weight will also be proportionally less. So its weight will only be 5 newtons instead of 30 newtons, and its acceleration will only be approximately 2 meters per second as opposed to 10 meters per second on Earth. And this is all due to the fact that that same 3 kilogram massive object has been placed in two different environments. Its mass hasn't changed, but its weight, which is due to the attraction of the object it's sitting on, like the moon or the Earth, has in fact changed. Now, in this slide, we'll try to reiterate what we've said earlier, perhaps in a different way to reinforce the difference between mass and weight. In this case, and what you see on the first statement, is that we use mass and weight interchangeably in the course of our transactions and our discussions while we talk about when we talk about certain quantities of food or fuel or things like that here on Earth. One example for might be we could say that, for example, that the weight limit of your baggage on an airplane is 50 pounds in the USA, whereas in Europe they might tell you that your weight cannot exceed 22 or 23 kilograms. This is basically what is translating mass into force, pounds being a unit of force, kilograms being a unit of mass. And the reason we're able to do that is because both measurements are made on Earth. And on Earth, we can draw an equivalency between, or a not an equivalency, but a conversion from pounds to kilograms. For example, we could say that with quite a degree of certainty that 1 kilogram of carrots weighs 2.2 pounds. And that would be an accurate statement. And we can use that conversion while we're here on Earth. But if we take that same pound of carrots and transport it to a different planet or a different object, such as the moon, then it would be only we can only say that the object itself has the same mass, but it will have a different weight, and that is due to the fact that weight it depends on where that mass is located, and the mass of the pound of carrots or the kilogram of carrots, I should say, is the same. The mass is the same on Earth as it is on the moon, but they will have a different weight. Therefore, we can say that mass is more fundamental than weight because it's a property that doesn't depend on where it's located. In this slide, we are rewriting Newton's second law in a slightly different form by saying that the acceleration is the net force divided by the mass. And an example of this is that if I double the force acting on an object, then the acceleration will double. That's clearly why an engine with more horsepower, but having the same weight as an engine of lesser horsepower, will accelerate, will cause the automobile to accelerate because it's generating more force on the same object. Therefore, it's giving it a higher acceleration. Now, the other way we can look at this is that if I keep the net force the same, so let's say I put the same engine from a Volkswagen Beetle into a Chevy Tahoe, then we can say that in this case that the force which is provided by the engine will be the same. But what is different is that the mass of the Beetle is much less than the mass of the Chevy Tahoe truck. So that means, or Chevy Tahoe SUV. So in that case, what will happen is that the Chevy Tahoe SUV will accelerate at a much lower rate than the Volkswagen Beetle, using the Volkswagen Beetle's engine. So, for example, let's say that the Chevy Tahoe weighs twice as much as the Volkswagen Beetle, then the force on it being the same, on the car, both cars being the same, the acceleration of the heavier object will be cut in half. Okay, now in this slide, we have two columns of different information, or two scenarios or experiments that we wish to carry out. We start at the top of the slide with a known force acting on the brick, which causes it to accelerate. We'll assume in all of these that there's no frictional force of the object, the brick, against the table, but only the force of the hand that causes the acceleration. So let's take a simple example. We can suppose, for example, that in the top left-hand case picture, we have, let's say, 10 newtons of force being applied to 1 kilogram of of mass of a brick. And by Newton's second law, what that means is I can calculate the acceleration, and the acceleration will be 10 newtons divided by 1 kilogram. Therefore, it will be 10 meters per second per second. And what that means is that the change in velocity, the increase in velocity after every second will be 10 meters per second. So at the end of the first second, the brick will be going at 10 meters per second. At the end of the second, it will be going 20 meters per second. And at the end of the third second, it will be going 30 meters per second. Increases 10 meters per second after every second. Now, in the second, the slide right below that, the picture, I should say, right below that, we look at the scenario where there's twice as much force, and therefore there'll be twice as much acceleration. So let's say now that I have 20 newtons of force acting on the 1 kilogram object. Now I have 20 meters per second of acceleration, which means now the velocity increases by 20 meters per second after every second. So at the end of the first second, it'll be 20 meters per second. At the end of the second, it will be 40 meters per second. At the end of the third second, it will be 60 meters per second. So that's what is happening there. In the third case, I now keep that 20 newtons of force constant, but I've also increased the mass to 2 kilograms. So in that case, the ratio of 20 newtons to 2 kilograms is again 10 meters per second, and that will have the same acceleration as the picture at the upper left hand of the figure where we started. Now, looking at the right column of the experiments, we again take our standard case. We'll take it to be 10 newtons of force acting on 1 kilogram. And now I add another block, which gives it 2 kilograms. Now, what has happened is that the acceleration is only 10 divided by 2, which is 5 meters per second per second. So the speed of the two blocks together will increase only by 5 meters per second at the end of every second. So end of first second, they're at 5 meters per second. End of second, 10 meters per second. The end of third second, they'll be 15 meters per second. So that's the acceleration in that case. Now, the final case here on the lower right is now I have tripled the number of blocks. So now I've got 3 grams. And I'm still applying, I'm sorry, 3 kilograms. And I'm still applying the same 10 newtons of force to that 3 kilogram mass object. So now my acceleration is 10 divided by 3, which is 3.33 meters per second per second. And so that's how we learn to use Newton's second law applied to acceleration of bricks.